Chiara is going to talk about cohomological field theory from Vertex operator algebras. Feel free to start whenever you're ready, Chiara.
Okay, thank you for the invitation, and I'm happy to present this joint work with Angela Gibney and Nicola Tarasca. And let me start saying that I'm an algebraic geometer. So I sort of use representation theory to deduce properties of geometric objects that I'm interested in. And today I will try to explain how these things works. And I will not assume much about algebraic geometry. I might assume more about vertex algebras, but as I said, it's more like a working knowledge than really, I'm not an expert of the representation theoretical part. So let me start saying that what is the main goal of today? The main goal will be to describe properties of some spaces which define some sheaves, which are called sheaves of coinvariants, which you can imagine as being, maybe you know what conformal blocks. So this will be the dual version. So the dual of the coinvariants are the conformal blocks. And I want to study the properties where the representation theoretical input that we give are modules for a vertex operator algebra. And let me say that every time I say MG and bar, I mean the moduli, where you can imagine as being a variety or a space, which parameterizes genus G curves, which have n mark points. And these curves might be nodal, so either smooth or nodal. So if you don't like curves, you prefer Riemann surfaces, this is okay, because this is a nice curve of genus 2, and I have maybe 3 mark points, and by nodal it means that I can essentially pinch one part, and so this is still has genus 2. But another way of making nodal curves is to take maybe 2 tori, in this case of genus 1, and they are joined together at one point. So these are all genus 2 curves for me. And I have to fix certain amount of points. Maybe I fix 2 in one components, 1 in the other one. And so a point in MG and bar is one of these elements. And so the spaces, the sheaves of covariance are constructing taking some geometric input, which is what I describe here, and some representation theoretical input. And what I want to describe today is how to construct these spaces, what are exactly the sheaves of covariance, and which properties they have. And I would like, the goal would be to say, okay, they define a cohomological field theory under certain conditions. So I want to start with the classical case, what I believe is the classical case of sheaves of coinvariants, which doesn't see it for the moment any vertex algebra. They're sort of hidden because the representation theoretical input is given by a simple Lie algebra, and I fix a positive integer and some, let's say, irreducible representation of G of a fixed level. So everything, I didn't say it before, but everything will be over the field of complex numbers. So you can use, if you want, your maybe some analytic intuition instead of algebraic. So I would like to construct, given this data, a space. How do I do it? Well, first of all, I like every time I have a Riemann surface or a curve, assume it's something like this, I fix my point, P. I want to go very close to the point and take a formal disk around it. If I take a formal disk, I can see it as being power series with coefficients in C, and P is a coordinate at the point P. So this represents, if I want to just see disk, I can use this ring. And I can tensor the Lie algebra, I can extend the coefficient, and this is another Lie algebra, which naturally sits inside another Lie algebra slightly bigger, where I can actually invert the coordinates. So this would correspond, let me maybe change the color, to the disk where I removed the point. I'm removing from the disk the origin. And we know that the affine Lie algebra associated with G is a central extension. Let me call K the center of this Lie algebra. We have to use the Killing form and residues to define the new Lie bracket. So this splits as vector spaces, doesn't split as Lie algebras. And there is a unique way to associate to the representation W of G, irreducible representation of this G hat, such that K acts as multiplication by L and is induced by G in the sense that elements of G acts as if they were acting by W, and that such that TP acts trivially. So essentially, I kill all powers, positive powers of TP, but I have some negative ones, which artificially exist there. And if I just induce the representation, will not be reducible, but there is a maximal quotient. So I can construct this. And so far, what I've done now, it's very local. There is no geometry. This is just the representation theory, if you want. But so where does the geometry comes? Well, I can consider the curve outside the point. So I can take the curve outside the point. This will be defined by some function. So this will be defined by, let's say, a ring of functions. Let me call it O of C minus P. For example, for P1, these will be all the functions which have poles at the point P, if I remove the point. And again, I can take the tensor product of the Lie algebra with this. I extend again the scalars. This maps naturally to the Lie algebra, which I extended, but moreover, by the residue theorem, it's also a Lie subalgebra of the affine Lie algebra. So the way in which I extend the Lie bracket essentially behaves well in such a way that it's really restricted to all the Lie bracket on this sub-Lie algebra. But then observe this space here has an action of G hat, but G hat has a sub-Lie algebra, which is this one. And so I can define the space of coinvariants, which, let me denote, I want to remember that I have a curve, a point, the algebra, the level, and the module. This will just be the quotient by the image of, essentially, I'm killing everything which is in the image of the action. So this is the classical construction of sheaves of spaces of coinvariants starting with the Lie algebra. And the name just tells everything. They're just coinvariants with respect to an action. And one can do this procedure also for nodal curves. And more generally, we can also consider more points and more representations. And the interesting thing is that one can always see that the points and the representation are associated. So every time I have n points, I also have n representation. And I really want to see that representation is associated at that point and essentially do the same construction. And the upshot is that these spaces are, they sort of fit together to define a vector bundle on the space MGN bar. And we can compute the rank. The rank was computed using the Verlinde formula. And I didn't write who to attribute this result because there are so many people who contributed. I would mention Tsuchiya Ueno Yamada, who defined these spaces, I would say, first, but there are contributions from many other people, and especially earlier results for genus 0 were already known by them. So this fact that the spaces are fibers of a vector bundle is interesting because it means that independently of which curve we have and which point we fix on the curve, the dimension of this space, so let me maybe write here, the dimension of these spaces, and let me just fix one point just for notation. So this is sort of independent really of C. We just, it depends on the, let's say, on the fact that I have a curve on the genus, on the genus of C, and the fact I'm choosing a point and a representation. And this is crucial together with a property which is called factorization, which I'm going to describe later. It's crucial to compute then the dimension of this space, of these spaces, and to study their properties. In particular, so these spaces have also other interpretation, which as spaces of generalized theta functions, and I will not go into this direction, but if you have more questions, I can address them. And if I have time at the end of the talk, I might talk about some open questions, which some of them involve also this classical sort of conformal blocks and coinvariants. So this is the classical picture. What I want to do is to essentially go beyond the Lie algebra world and go to the vertex operator algebra world. So I want to essentially replace the representation theoretical input, which was the algebra representations, with vertex operator algebras and V modules. This might not be very surprising, and it's not something that my co-authors and I thought one day, let's do this. Many other people have worked in this setting. And before mentioning a couple of names, I want to see why actually this situation is a natural subset of that one. And I will say in a second what I mean by vertex operator algebra and by modules, but what I want to say now is that every time we have G and a level, there is a natural simple vertex algebra associated to it, which, if you want, it's exactly what before I would call M bar C. So it would be the representation of the affine Lie algebra associated with G associated with the trivial representation of G. And again, to the module, if I have a representation of GM, I can associate this module which I had before and bar W, and this is really a V module, where V was this vertex operator algebra. So, and the way in which we will construct the coinvariants for vertex operator algebra naturally generalizes the construction for simple Lie algebra. Now, let me mention that maybe the bit of history here. So I have the feeling, but I find it a bit hard to find the literature, that the definition of Cohomological or conformal blocks over P1 is sort of known. These are just correlation function, intertwining operators. It's something that at the level of representation theory, it's well known to understand how these spaces are. Essentially, over P1, there is really no geometry, really. It's going on. It was already known how to define these spaces over, in certain cases, over smooth curves. So the definition of the sheaves of coinvariants was given by, for example, Frankel and Benz-V. But it was not extended to the nodal case, and not many properties were analyzed. However, on M0 and bar, so rational curves which are nodal or smooth, both the definition and properties were analyzed by Nagatomo and Tsuchiya. And I would say that essentially the global picture really on MGN bar, considering higher genus and also nodal curves, was given the definition, understanding their properties, and some maybe application, well, maybe not application, but let me say computing the CoFT. This was done by my co-authors Angela Gibney and Nicola Tarasca and myself, in full generality, and it's based on some works, some prior works that I described here, but essentially put everything together. And I think now we have, especially from an algebraic geometry point of view, enough structure that we can actually use these objects to do some algebraic geometry. So, and as I said, we work in the algebraic geometry setting. I know that recently some properties, for example, the solving property for conformal blocks that we proved was proven by Bingui in the analytic setting as well. So I think it's a field where many people are working on, and there are so many different perspectives that I think it's very hard to keep trace of everyone working in this field. So I apologize if I forgot any name. So what I want to start is, let me maybe briefly say what I mean by vertex algebras and by modules. Or are there questions? Okay, so by a vertex operator algebra, I mean a graded vector space which has two special objects, one in degree 0, one in degree 2, called the vacuum vector and the conformal vector respectively. And to every element of this vector space, I want to associate a family of endomorphism. And the way I associate it is through this map that I usually called Y, which is called the vertex operator or the state field correspondence. Of course, there are some axioms which must be satisfied, which I will not write here because we are not going to use directly in the talk. But what I want to emphasize is the fact that we will further assume that each graded parts, each VI is finite dimensional, and that the vertex algebra is chiral, meaning the V0 is only one dimensional. So very often these conditions is called, we say the vertex operator algebra is of CFT type if these conditions are verified. And by module, I mean, again, a vector space, which is written as a direct summon of subvector spaces, which are indexed, which are non-negative. But it's, let me see, it's graded over the integers. Again, I have a state field correspondence, which associated to an element of a family of endomorphism. And I want that the similar way in which the Virasoro algebra, and I guess we all know maybe what that is, but otherwise I can talk about it later. Well, we need this conformal structure that omega induced on V to also induce a conformal structure on M. And we further assume that the modules also satisfy the property that each component is finite dimensional, and then the action, maybe this would be more correct to put an M here, the action of V on M respects the grading. So sometimes these modules are called admissible modules in the literature, and most of the time we will actually use simple modules. And so when the modules are simple, things will become easier. I mean, but I will talk about this in a second. So this is more or less the input that I have. And if you don't know what the vertex operator algebras are and what the modules are, I would really like to imagine thinking V is sort of like a like in the case of affine Lie algebras, it's not hard to describe what V is and what M are. And there are some natural way in which we can associate V to, for example, an abelian Lie algebra, so obtaining the Heisenberg, or given an even lattice, we can associate a vertex operator algebra. There are many examples. But I will not have the time, and I think it would be maybe for me too complicated to write down some example, and there will be a lot of time spent there. So what I want to instead say is briefly construct the spaces of these coinvariants. And this would be a similar idea that of the coinvariants that I described at the beginning. So I would like to construct them as being a quotient of the modules by a certain Lie algebra, which encodes the geometry of the curve and the point that I fix. So in the classical case, it was easy. My Lie algebra was just, I had a Lie algebra to start with, and I just tensored with the ring of functions of the curve minus the point. Here the situation is more complicated, and let me say that you can have it's just more complicated. So how do we find a Lie algebra? First step, so the first step is to consider a coordinate-free version of the vertex algebra V over C. So this coordinate-free version, if you want, over every point is V, and over every point we have also the map Y, but the construction should forget that we fix a point at each coordinate. It's possible to do so. We need the conformal structure. We need the Virasoro action to do so. And moreover, it's natural that in this case, this is sheaf is equipped with a map, which is a connection. If you want to see it in coordinate, this is the same as a map from V tensor with Laurent series T to Vt dt, which sends an element a, let me say, f of t to L minus 1 a f of t dt plus, we don't really need this dt, but I prefer to have it, a df dt. Okay, so it's a coordinate independent version of this map here. And why do I need this? Well, because I can consider the quotient of this map. So I take V tensor omega, quotiented by the image of nabla, and this is a sheaf which I can evaluate on the curve minus the point. So I use this notation. So this will be the section of this sheaf over the curve minus the point. And I say that this is, I define the Lie algebra that I want in this way. This has a Lie algebra structure. Okay, and now we have to understand, how does it act on M? At this moment, okay, I have this object. Why should it act? Well, again, let's take maybe a picture. So I had the point P, and here I'm taking I take the curve minus the point, but I can ask for less. I can ask for just the disk, a very tiny disk around the point where I remove the point itself. And this is dp with a star. It's a disk around the point minus the point itself. And this is, let me call it L of V, is a Lie algebra. There is a natural map by restriction of section. And this naturally acts on M. Well, not really. Up to choose a coordinate at the point P, this is isomorphic to a quotient of, if you want, it's a quotient of this space here, put this nabla, and this acts on M, right? So we would like to act on M, but we can only act on M up to a choice of a coordinate. And let me maybe mention, how do I act on M? Well, the equivalence class of an object here, so it can take at to the n as one of the generators. This will act on an element m in M as the endomorphism associated with A and with N. So this was in the notation of the state field corresponds for modules. So maybe to wrap this up, what we showed is that this Lie algebra, up to a choice of a coordinate, acts on M. And so we could define the space of coinvariants depending on a coordinate as this quotient. Well, this is almost what we want. We would like to get rid of the coordinate. The reason why we don't want the coordinate is because at the end of the day, we really want to only take care of the curve and a point. We don't want to fix other data. We want to be on the moduli space of the curve with points, not of points and coordinates. But this is possible to do. You can essentially descend this construction forgetting the coordinate. A way to do so, maybe just point-wise, would be to construct again, a coordinate-free version of the module M, so that at the point P, the fiber of this space is isomorphic to M if I choose a coordinate. And depending which coordinate, you have other identifications, but the Lie algebra LCPV will act on MP without a choice of coordinates. So there is a way to construct it. And so, for example, we can define it in this way, in a coordinate-free manner. So I don't want to spend too much time in this. There are some technicalities involved, but it is possible. And so one of the first results with my co-authors is that this can be also done with nodal curves. Of course, the point P is always smooth. So every time you have marked points, they're always smooth, that you might have nodes somewhere else. And we can do this construction not only for curve, but for family of curves. Everything works nice. And this defines a quasi-coherent sheaf on the moduli space of curves of genus G with one marked point. And this sheaf, we call it the sheaf of coinvariants. And so we only denoted with the G, which emphasized what was the genus of the curve. And the dual is a sheaf of conformal blocks. And this is just a side comment. The reason why I study property of coinvariance instead of conformal blocks is that from this perspective, coinvariants behave more nicely than conformal blocks, because conformal blocks at this point, we don't even know whether they are quasi-coherent or not. So the dual of quasi-coherent sheaves can be very bad. We will see later that under certain assumptions, they're vector bundles, they are beautiful. So we can work with one or the other one. But in general, coinvariants exist, and they are sort of slightly nicer than conformal blocks. And let me add a couple of comments to this result. Well, the first comment is that we could have also taken more points and more modules, and we would have had another sheaf on, MGN bar. Actually, I will maybe say something later. We need, for some stability condition, when the genus is very small, we do need to have many points to construct the sheaf. Then we show that we didn't care. We could have taken just one, but we need to have more points in general. The other observation, which was observed already by Frankel and Ben-Zvi, and I believe also from maybe other people, is that if the vertex operator algebra that we started with was the one associated with G and level L, then this construction recovers the classical coinvariants and conformal blocks. But, and I want to emphasize, but a priori, the Lie algebra that we started with, so this is not equal. So we are modding out by different Lie algebra. They give rise to the same coinvariants. Because of the residue, we can go from one to the other one, the residue theorem. But if you want here, I really have, there are some forms, there are some differential forms appearing. Well, here you only have functions. So in this case, it works, but in general, you really need to use some differential forms of some types. And there are other types of, there are other Lie algebras that have been used to construct coinvariants. And they even if
Can I quickly try to understand the G tensor with the O, C with P removed? And if I take the projective curve, so that's basically just the polynomial algebras with T inverse. Am I correct?
If you have P1.
Doesn't have the positive power of T.
If you are on P1, yeah, so OC minus P is really T minus
T
1.
inverse, yeah. Okay.
But you can have more complicated curves, but you will always have poles. You might have 0, but you can also have poles there. So if you take an elliptic curve and you remove the point at infinity, for example, you will have something like, it's a bit more complicated. So we don't really have one coordinate.
Yeah, thank you.
You're welcome. Are there other questions? Okay, and the last property I want to talk about now in this series of remarks is that, as in the classical case, these spaces are naturally equipped with a projective connection. And I put in parentheses that they are logarithmic singularities along the boundary. But if you just consider smooth curves, it's sort of already embedded in the construction that these spaces have this projective connection, which is a property which can also be expressed in a more refined way using the language of Atiyah algebras, but it's fundamental to have an explicit description, for example, of Chern classes. So it's very important. We might see it later. So the title of this talk is Cohomological Field Theory from Vertex operator algebras. So what do we need to define a cohomological field theory? What do we need? And this is sort of, let's take a step aside. We need a finite dimensional vector space, which has a sort of unit element and which has an involution so that the unit element is sent to itself. So once we have this data, and at the moment, well, I used V, but in general, there's no relation with Vertex algebra at the moment. A cohomological field theory is a collection of maps that is indexed on G and N. G will be a genus of a curve, N is the number of points, which associates, which takes N of this element in this vector space and gives back some element in the cohomology ring. So this will be just the direct sum of the cohomology. If you think about singular cohomology, this works. And all these maps there can be some relations because you have maps between different moduli spaces, for example, for getting some points. And when these maps satisfy some compatibility conditions, this defines a cohomological field theory. And semi-simple cohomological field theories have been classified. And what we would like to do is to sort of construct a cohomological field theory where the space W is the space of, let's say, space which basis is the set of simple representations of V. And the involution just sends a module to the contra gradient. Which just means the direct sum of the dual of each single piece. And the unit element is the module, is the vertex operator algebra itself. And we would like to say that if we take this condition, then, and suppose I start with the simple modules M1 to Mn, how do I define this cohomological field theory? I take what's called the Chern character of the space of covariants. associated to these modules. Well, let me just observe.
So can I say just understand W is the grothendieck group of the representation category of the vertex operator algebra V?
Can you repeat?
Can I understand the W here is just the grothendieck group? Then you just tensor with whatever field, make it a vector space.
Yes. Yes.
Okay. Okay. Thank you.
Yeah. Yes. Yeah, and if you don't know what Chern character is, it's okay. Just you can imagine that we just care about the rank of these spaces, so the dimension, if you want, of a fiber. And we already see that at this moment, we don't even know whether this is finite. So we need to have extra condition on the vertex algebra and maybe on the modules that we take, so that first of all, we have finitely many simple objects and that they determine everything, and that these spaces can actually make sense to compute the Chern character, so that the rank is finite, for example, or there is a well-defined rank which does not depend on the point where I am. So, so I need to add extra condition to be sure that this is well-defined. So the conditions that we want to impose, and that this will lead to the main result of the day, are first of all a finiteness condition. So we already said that we want our vertex algebra to be of CFT type, and we further require the Joule's finiteness condition, so the fact that V modulo C2V is finite. This is, I believe, a very standard condition to impose on vertex algebra. And the second condition is rationality. So this controls the representations of the V modules. So we, imposing this condition, we know that there are finitely many simple modules, and every module of V is just a direct sum of the simple object. So if you want, it's similar to having representation of semi-simple Lie algebra. I know that, or representation of the algebra, I know that I can just construct them starting with the simple ones and take direct sum. And together with my co-authors, we said that a vertex algebra with these properties is of coFT type. We couldn't find in the literature a name which identified a Lie algebra, vertex algebra having these conditions. We do not assume that V is self-dual, for example. Very often this is a condition that it's used. We do not use that. And we just call it of coFT type because, as we are going to see in a second, with these conditions, we define a cohomological field theory using the Chern character. So let me state the theorem, which we proved with Angelo Gimli and Nicola Tarasca. And this says that if I start with a vertex algebra of coFT type and the modules and n modules which are simple, then the sheaves of Covacqua are actually vector bundles of finite rank. So this is the first part of the theorem. And I want to mention that the finiteness of the rank only needs part A. We don't need rationality to show that it's finiteness. While to show that they are vector bundles, and let me use this pink color. Well, if I only need to show that they are vector bundles on MGN without the bar, so on the open locus, it's enough A and the projective connection that I mentioned before. This is a standard thing that every time you have essentially a coherent sheaf, so something finite dimensional, and we have a projective connection, your space is actually a vector bundle, meaning it's locally free. But for MGN bar, to extend this this property to the boundary, we need both A and B. And in particular, to show this, we use the sewing theorem, which it's a refined version of the factorization theorem. And I will say a couple of words on factorization later. So to show that they are vector bundles and their finite rank is sort of very important. And already the sewing theorem and the way in which we prove this are key ingredients to conclude the statement of the theorem that says that we can really compute explicitly the Chern character, because this assignment, as I said before, take the modules and I compute the Chern character, is a semi-simple cohomological field theory. And I want to say that the idea of computing Chern characters of these types of bundles of coinvariants, using cohomological field theories, I learned this by from a paper of Marian, Opria, Pandaripante, Pixon, and Zwonkine, where they actually use this method to compute Chern classes for the classical sheaves of coinvariants. And essentially, we show that the properties that they use still hold in this setting. So I know I do not have that much time, but let me maybe add a couple of comments on the proof and say, okay, what are the properties that we actually need to show that determines the co-FT? And well, the first two properties are sort of standard, I would say. So the first one says, if I am on P1 and I have one insertion which is trivial, and the other two that are two modules, then these spaces are either one-dimensional when the modules are one dual of the other one, or it's zero-dimensional if this doesn't happen. And this follows from fusion rules. So this really follows, we use the description of the conformal blocks instead of coinvariants. So here we really use we can go back and forth between studying conformal blocks and coinvariants. For propagation of vacua, this just means that, let's forget for this P for a moment, that I can always add an extra point where I insert the adjoint representation V, and my space doesn't really change. So this P would be just a map from mgn+1 to mgn, and it is that if I have a space here, which forgets the point. So I start with the sheaf here and I pull it back, it was the same space that I obtained adding a point and adding the trivial representation. And let me say that the propagation of vacua is actually needed to define the objects. We need to define the objects. I need to be sure to have enough points. And so the strategy is that, well, I can add as many points, I put the trivial representation. So it's really, I have the feeling that it's sometimes underrated, but I think it's extremely important. And it was already proven in certain cases by Frankel and Ben Zvi, and also Giulio Codogni wrote a more general proof, and we combine a bit both things. And we need here that V is chiral and a CFT type, for example. We don't need that the modules are simple, but we needed the vertex algebra is nice enough. But the main property is factorization, which essentially tells us how these sheaves of coinvariants or spaces of coinvariants really naturally decomposes when the curve they are attached to is nodal. So, and let me do a drawing. So I start with a curve, and for simplicity, it has only one node, and it's only marked by 1 point. So I start with this, and I can construct the space of coinvariants where I fix just one representation M at P. What I can do is that every time I have a node, I can sort of blow up the curve. And essentially what I imagine is that I'm cutting and pasting. I'm cutting the curve at Q and I'm blowing it up so that I add 2 extra points. Or if you want to go backwards, every time I have a curve with 3 points, I can choose 2 and glue them together to get a nodal curve. So this new curve, let me call Cn for normalization, is now marked by 3 points. And well, at the point P, I had a module M, I can put the module M. But now what should I put at point Q plus and Q minus? Well, if I choose a simple module W at Q plus, I want to choose the contragradient at Q minus. Essentially, Q plus and Q minus, since they come from normalization, they are related somehow. And the way in which we can relate them from a representation theoretical point of view is in this way. And so again, I can construct another space of covacua or of coinvariants. They are sometimes called spaces of covacua in this way. Where this is the control gradient. But again, here, what is W? Well, I can take the sum over all possible simple representation, which are finitely many because by assumption our vertex algebra was rational. And the theorem tells me that this is isomorphism. So we can always decompose the space over a nodal curve as a direct sum of spaces where the geometry is simpler, but there is more representation going on. And you can even go further and see that essentially if you take a very degenerate curve, every time if you care just about the dimension of these spaces, for example, you want the rank, you can always take a very degenerate curve because after many normalization, you end up only with a lot of P1s, which have only 3 mark points in each component. And so the computation, not only of the ranks, but also of the Chern classes really boils down to know what happens on P1 for the ranks. And for the Chern classes is a bit more, it's essentially induced only on the open part with the projective connection. So, so maybe let me just say that, as I said before, a refined version of the factorization is what I sometimes call Sowin theorem, which I want to just say that essentially there is a way in which we can deform a curve. So I start with a curve and I perturb it a little bit. And if I do it, and there is a very natural way in which you do it so that your perturbation gives something new. But essentially this perturbation doesn't change the spaces of covacua. So it just extends them by scalar because I start with a curve and I sort of make them a bit thicker. So I have a family of curves, but the space of covacua doesn't really change it. And I use here vacua to mean really coinvariants or conformal blocks. It will take too long to write this, the statement because I have to explain what is this non-trivial deformation. But this can express also saying that I can sew conformal blocks together, starting with a smooth curve with 2 mark points. If these 2 points are identified in a specific way, or they just identify neighborhood of them, I really know how the conformal blocks behave. And we need this theorem to show that these spaces, these sheaves are locally free. So in the remaining 2 minutes, if I'm not mistaken, I want us to talk about some open questions that I'm interested in. The thing that I find interesting is having a modular interpretation of conformal blocks. So something that I didn't mention is that if I have a curve upon the Lie algebra level, and let me take the trivial representation, and I take the dual of the coinvariants, meaning the conformal blocks, this is a space of global section of a certain line bundle on a modular space which parameterizes G bundles, where G is the simply connected group whose Lie algebra is G. So essentially, I can deduce information. I can study, this would be called generalized theta functions on another moduli space. So this is another moduli space which is associated with G and the curve C. I can study this other moduli space. I can do other algebraic geometry using these spaces. And the question is it possible to do similar thing when the vertex algebra is more complicated? Well, it is possible when the vertex algebra is again given by G and L, and I add extra modules. this will lead to parabolic bundles. And it has been shown that it's also possible when it's a Heisenberg. But beyond this, it's really not, I don't know anything of that. So we'd be interested to know this. And other questions they have are other geometric properties that holds in the classical cases. So let's restrict to genus 0. What can we say more about these spaces? And a twisted version of it. So we know that we can construct twisted coinvariants from there are some construction of orbifold modules and orbifold conformal blocks. There is a construction of twisted conformal blocks I've carried out in my PhD thesis, just using representation of Lie algebras and coverings. Are these two notions the same? Can we go beyond and study more properties? But I think since my time is up, I think I just want to thank you all for the attention.
Thank you so much, Chiara. If you have questions for Chiara, please feel free to unmute yourself and go for it. I'll pause the recording now.